Welcome you all to the video lecture of Introduction of Electrical and Electronics Engineering. So we are going to get continuous over to that of our previous video lecture regarding to that of the AC fundamentals. So in the previous video lecture we saw the terminologies of the AC circuit. Now we are going to discuss about to that of the law of electromagnetic induction. So it also comes under to that of the course outcomes CO1. So where we are going to just apply those losses and simplify the techniques into that of the electrical engineering with respect to that of the electric circuits. So first we are going to see that how we are going to get determined over this the magnetic effect with respect to that of the electric current. So there will be two rules as said to get determined these things. So first one is the right hand gripping rule and the next is the right hand corkscrew rule. So with respect to these two rules as we are going to get determine this magnetic effect of the electric current. Okay, now we are going to get consider a conductor. So here there is a conductor, it has some electric current flows over to that of conductor. Okay, so this is the first point. So next is the conductor's length. So the conductor's length is that what means the magnetic field. So the magnetic field is get set up upon with respect to that of the conductor's length. If suppose there is a conductor, so here this conductor has some length, so this length will be get defined by using this of the magnetic field. So this magnetic field is also get set up along with respect to that of the length. So conductor has a electric current flow, so magnetic field. So now the electromagnetic lines of the forces. So the magnetic lines of forces will be obtained how means in the form of the concentric circle. So here this turns says to that of the concentric circle. So this concentric circle says to that what? The magnetic lines of force. So now this directions of the lines of the force where we get dependent to that of what means the direction of the current. So with respect to the direction of the current, the direction of the lines of force also we get defined. Okay, now we are going to discuss what is meant by the right hand gripping rule, right hand corkscrew rules. First, the right hand gripping rule. So let us consider we are going to get in the right hand. So in that right hand we are going to get gripped over the conductor in that right hand. Here that the thumb direction says to the top the direction of the current. So the direction of the current is defined with respect to the top the thumb pointing. So the remaining rest of the fingers says to the top the direction of the magnetic field. So here the thumb and there is a conductor. So here these are the fingers. So this other fingers is going to be says what? The direction of the magnetic field. So the direction of the magnetic field. So this thumb says to the what? So thumb says the direction of the current. So the next is the right hand corkscrew rule. So this right hand corkscrew rules deals to the top the direction of the magnetic field is what means the direction of the rotation of the right hand corkscrew. So with respect to the top the right hand corkscrew is get directed towards to the rotation of the right hand corkscrew. So I am clearly saying that this the direction of the magnetic field is what means that of the direction of the rotation of the right hand corkscrew. If suppose the direction of the right handed corkscrew is get turned means the direction is all of the magnetic field or is obtained vice versa to that of the right hand corkscrew. So in order to say that to advance along with that of the wire in the current direction. So before entering to the further topics in this electromagnetic induction, here we are going to see some factors with respect to that of the magnetic effect of the electric current. So the first factor is the greater the current through the conductor, it results means what it results? Stronger the magnetic field. So if the current is high means the magnetic field is also strong. So this is the first factor. So the next factor is the second factor is said that the magnetic field is stronger near to the conductor and it is weaker and weaker when it is moved away from the conductor. Let's for an example, here there is a conductor, this is the conductor. So if there is a magnetic field is high in this point, so whereas in this point the magnetic field is low comparing to this magnetic field. So whenever the conductors nearer to the point is having the higher magnetic field, the faraway point has a lower magnetic field. Then regarding to the shape of the conductor, so here this shape of the conductor will tells us the pattern of the magnetic field. If it is in the circle means the direction is in the circle's way. If suppose it is in the rectangle means that shape defines as what, the pattern of the magnetic field. So another two factors is that here we are going to have the two conductors, so conductor A and conductor B. So here we having this two conductor. If suppose and another constraint is it has same amount of the current. Here I am having 2 amps of current, here also having the 2 amps of current. If the amount of current is in the opposite direction means what it results means there will be a no magnetic effort will be produced. If suppose they are in the same direction, it says is what, the twice is the magnetic effect and causes more magnetic effect is will be get produced. If they are in position to the top opposite direction, which means that side by side to the top opposite direction means there will be no magnetic effect is produced. If they are in the same direction, it has the twice the effect cost to the similar to that of the previous conditions. So these are the 5 factors we need to be keep in our mind before considering to that of the magnetic effect of the electric current. So now we are going to further deal to that of the electromagnetic induction. So now we are going to have the current carrying in the conductor in the magnetic field. So the current is carried over to the conductor where in a magnetic field. So let us consider a conductor. So this is the conductor and it get placed in the to the top the right angle. So right angle means what? So right angle says us to the of the 90 degree. So this conductor is placed in the magnetic field at with respect to the of 90 degree condition. Okay. So then the another thing says here when it is placed means here it has what? So I, B, and these are the parameters says us going to the top how this current is carried over to the top conductor. So here this I, L and B tells us what means the force. The force is the force F is defined with respect to the top B, I and L. So this B, I and L is what means the B is the flux density of the magnetic field. Here this is the magnetic field. This magnetic field is defined from where? The letter B. So B is what means the flux density of the magnetic field. L. So L is what means the effective length in meter of the conductor which is immersed in under the perpendicular to the top field. So this L is defined to the top this length of the conductor. So and the I is obtained from the current where across the conductor. So conductor's current. So by the law of interactions, which means that I am interacting these B, I and L, there it says what the conductor will experience a force when it combines with that of flux density, length of the conductors and the current across the conductor. It produces what? A force. That forces will be acting in the direction to the top perpendicular to the top both where the magnetic field and the current. So F is equal to the force is obtained from B, I and L. So in to the top the relative term, if this is the relation where it will get true only when the conductor and the magnetic field are in to the top right angle. So the conductor and the magnetic field will be placed into the top the right angle. At this condition only this relation is F is equal to B, I and L will get be in the top positive, which means in the top the true condition. If suppose it is inclined at an angle some values 20 degree, 30 degree, 40 degree, Q to the top angle to the top magnetic field means then the length of the conductor is normally to that field. So then the equation F is equal to B, I, L into sine theta. So here this angle is obtained with respect to that of Q. So if suppose the relation F is equal to B, I, L, if it get true means how it will get true means it when it is placed to the top the right angle to the top the conductor on the magnetic field. If suppose it is not means then the relation is going to be changed over to F is equal to B, I, L sine theta in terms of Newton. Okay, the next rule. So now we have the clear idea to what the three terms is right hand gripping rule, right hand Crockery rule and some factors related to that of the electromagnetic induction. Now we are going to for the Fleming's left hand rule. So in our higher secondary classes also we have some knowledge regarding to that of this Fleming's left hand rule in that course physics. So let us consider the left hand. So three fingers, so thumb, middle and the forefinger. Here this three fingers related to the top three parameters. So the motion of the conductor, magnetic field and the current. So the thumb finger related to the top motion of the conductor, forefinger says to the top the magnetic field and the middle finger says to the top the current. So let the forefinger is what it is says to the top the direction of the magnetic field, so north to south condition, whereas my middle finger is pointed towards to the top the direction of the current, and followingly thumb finger says what the direction of the motion of the conductor. So this is what the Fleming's left hand rules. Okay, so further to the top there will be some losses obtained where with respect to this to electromagnetic induction. The first law is the Faraday's law and followingly the Lenz's law. So now we are going to see what is meant by the Faraday's law. So whenever the magnetic flux will get linking in a circuit, there will be change and EMF is also be get induced in it, which means that the magnitude of such an EMF where it is in the proportional state to the top the rate of change of the flux linkages. So then the Lenz's law is also states to the top any induced EMF will be get circulated along in a current in such direction, so it will be get opposed the cause of producing it. Okay, so let us for an let us consider the Faraday's law. Here let us consider a voltage. So that voltage is related to what? The electromagnetic force. So if suppose a voltage is created in an wire, means whenever the magnetic field changes around itself, so magnetic field changes around means what? It automatically says to the top the change in voltage, or it get produce some voltages. So this is what the Faraday's law. So and then Lenz's law, what it says means it says that any induced EMF will be circulated a current in such direction, so it will automatically get opposed to the top causes producing it. So this Lenz's law says us, which means that it will produce or it will gives us the nature of the induced EMF. Okay, so the magnitude of an EMF produced is proportional to the top rate of change of flux linkages is Faraday's law. So and the Lenz's law says what? The EMF will be circulated along the current. Okay, so let us consider here an isolated coil. So where the terminals are connected to the top the galvanometer. So here we are going to have some coils. So these coils get connected to the galvanometer. So then initially they are placed close to the top of magnet. So here this N and S says to the top of magnet, which with respect to the position 1 and 2. So initially it is in the place here. So now it get changed to the top 3 and 4th position. It will be say in the further presentation. So while it is placed in the position of 1 and 2 condition, which means that here the magnet is initially placed in this position 1 and S is 1 and 2, 1 have the north pole and 2 have the south pole. So here what the galvanometer and the coil is get coiled over some conductor, and here also galvanometer has been placed. Here the magnet is in the position or this position. So now the fluxes will from the north pole of the magnet will be get connected over to this coil. At this time there will be no deflection in the galvanometer, which means that it have the zero deflection. So zero deflection means here that point will not get moved to in that galvanometer. If suppose it will get positioned in the 3 and 4th position, which means that the one will get slighted to the top left side, and parallelly the second position will also be get moved. So it goes for the new position 3 and 4th position. So at that time there will be sudden change in that of galvanometer. Here in that galvanometer then and it will have some changes. So initial condition in that position of 1 and 2 it doesn't have any change in the galvanometer, whereas it get changed to the top 3rd and 4th place means there will be some deflection in that galvanometer. Okay, how this occurs when let us for an example, if a magnet is in a motion, there will be some relative to that of coil, it has some deflection. Now we are having get cleared that the flux linked with that where the coil. So if the coil is increased due to its approach. So okay, the next, suppose that consider the magnet is suddenly withdrawn away from that coil. So what it have, some there will be no monotony deflection in an opposite direction. It also says us to that of persist with the, as long as the magnet is in the position and the flux linked with the coil is get decreased due to that of a withdrawal of the magnet. Okay, so continuously we say that the same results will be obtained when the magnet is in the stationary condition and the moment conditions, or which moment condition means moving towards us to the tough coil, so with respect to the tough magnet. So and finally we are saying that whenever the magnetic flux linkages means a conductor will changes and what, an emf that the conductor will changes an emf with respect to that of inducing themselves, and its magnitude is also get dependence to that of the rate of change of flux linkages with respect to that of coil. So okay, so let us have this expression. So E is equal to that initial flux linkages and the final flux linkages. So N is the number of turns, so magnetic flux psi 1 and psi 2. So N relates us to the top number of turns in the coil, so initial flux linked in that coil and the final flux obtained in that coil. So T says us to the top what, the time taken in seconds for what creating the change in the flux. So N psi 1 minus N psi 2 divided by T. So here the number of turns will be same when initial condition also and final condition also, which means that so initial flux, magnetic flux condition also the number of turns will be same. Here they are considering the same coil only, not different coil. So automatically, so E is equal to N into psi 1 minus psi 2 divided by T. So the magnitude of the average induced EMF E is equal to N into psi 1 minus psi 2 divided by T volts. So continually with respect to that of incorporating this Lenz's law, the equation get changed to E is equal to minus N d psi by dt, which means that with respect to that of time, differential time, there will be some differential flux is also be get induced. Okay, so how this minus n get be produced mean, after incorporating this Lenz's law only this minus term will get be induced, or else normally the induced EMF E is obtained with respect to that of N into d psi divided by dt. So flux, so differential with respect to that of flux with terms to that of T. So after inducing the Lenz's law, so minus N into d psi divided by dt volts. Okay, so now we are going to get considered to the top the Fleming's right hand rule. So here the thumb says to the top motion of the conductor, middle finger says to the top EMF, and the forefinger says to the top the what, magnetic field. Whereas in the right hand rule the forefinger says what, magnetic field. Here also what, the same magnetic field. Thumb conductor in the left hand rule, and thumb same right hand rule also having the same conductor rules. Whereas the middle finger here in the left hand says to the top current. Now in right hand rule it says us to that what, then EMF. This is the different term. Here in right hand the middle finger says to the top what, EMF, the direction of the induced EMF, which means that the EMF get induced after what, after the magnetic field with conducting to the top of a conductor. So here the middle finger is the EMF, inducing EMF. Okay, induced EMF. So here if suppose there is an EMF is obtained or get induced into a coil or a conductor, it says us whenever there is a change in the flux linkages, this change in flux linkages can be brought, how means there will be a two condition. If conductor is in the movement condition, stationary condition. If suppose the conductor is moved means then in a stationary magnetic field. So here the magnetic field is in the stationary condition, so conductor is in the moving condition. So in such manner the magnitude, so height will be changes in terms to that of flux linkages. So this kind of induced EMF is known as the dynamically induced EMF. Examples such as to a generator. So next is the conductor is in the stationary condition and the magnetic field is in the movement condition. So this is known as what? This kind of induced EMF we are going to say is a statically induced EMF with respect to that of transformer. So the transformer and generator. So generator having the conductor is in the moving condition, and whereas the parallelly the stationary term is the magnetic field. Whereas in the transformer the magnetic field is in the moving condition and the conductor is in the stationary condition. So this clearly says us what is meant by an induced EMF. Okay, so the dynamically induced EMF and the statically induced EMF. So this is the before considering we need to see here for the dynamically induced EMF the conductor and 90-degree angle minus to the top of the theta terms. How there here in the dynamically induced EMF, what is the condition? The conductor is to be get moved. If suppose here this conductor, here this point, it has some round radius, it has some radius, it has different radius, so the radius will be get deferred in with respect to that of various points, which means that with respect to that of various deducting motion. So with respect to that our equation, so induced EMF is equal to BLV sin theta will be obtained in dynamically induced EMF, whereas to that of a statistically induced EMF it says us to that here the conductor is in the position of a stationary, whereas the magnetic field will be get varied. If suppose here there will be a two coils get circulated over to that of A and B terms as a. So now the coil 1 is energized using some batteries. So here this is the battery, here this coil A get energized. So then if switch K is initially closed, then the steady current will flow through the coil A. If it is in the closed condition, the steady current will be flow towards the coil. So the linkages will be in terms as obtained from the psi 1. So with respect to that, such EMF get initially produced with respect to the statistically induced EMF, then it is known as a transformer EMF also. So now it is get be classified into two categories such as self-induced EMF and mutually induced EMF. So the self-induced EMF will be get related to the top term E is equal to d psi divided by dt. So here this direction of this induced EMF will be in that condition to the top of opposing of any change of flux which will be very close causes to of its production. Here it is also known as to the top opposing or counter EMF of a self inductances, whereas the mutually induced EMF is that the thing whenever there will be a change of flux linking in it, the flux being produced by the current in the another circuit with respect to that of the below figures. Here suppose we having that the same phenomena can be observed in that where A and B coil when it get energized. So with respect to that of term the self-induced EMF and the mutual induced EMF, we are going to get having some clear idea regarding to that of what terms. So statically induced EMF, whereas the dynamic says to the top with respect to that of motion position, the dynamically induced EMF will be obtained with respect to the top term E is equal to BLV sin theta. Here the equation term we are going to get considered over is E is equal to N d psi, which means that differentially with respect to the of time the fluxes will be get deferred. So this is the main thing we need to be get considered over there.